Whichever master's it is a graduate student. And similarly, I don't care which student, whether graduate or undergraduate, are all UB students. So we started with a whole sample of UB students. We were talking about lab access, and here was a structure that helped us, define this lab access. So it helps us categorize, first identify, and then organize in whichever categories we are looking at. Okay, so that is the first look at inheritance and how it becomes a technique or form of generalization. So it says the commonalities are organized into a tree structured form. At the root of any subtree are found all attributes and behavior common to all of the descendants of that root. And then you have a slide of a similar slide of a student hierarchy. Then you say, what kind of characteristics does a hierarchy have? So this structure here is known as a hierarchy. So when we look at characteristics of a hierarchy, we say it's a form of knowledge representation. That's one. Okay, and that applies to us also, but is not the only field that it is applicable to. You would have seen organization charts like this. It could show in a company who is at the head, and then which could be the president, then the vice presidents, and then the managers, and so on and so forth, kind of a thing. So you might have seen it outside software. It's not, it's only, we are not the only clients to this. It has, but what is very interesting also about it is that it is extensible. So let's say we start a new master's in aeronautics engineering. All I have to do is add it at the right level. I did not have to change anything here. Let's say the school has a new, the university has a new school, let's say a school of medicine. Do I have to change anything in this whole thing? No, just add another school here. Right? Assume we wanted a third category of students as doctoral students. We don't count them, we don't want to count them in graduate anymore. We want a separate category. What do? Just add it here. That's a very important and very useful characteristic, because when we make our own hierarchies, right, when we code our own hierarchies, that is something that we will tell you is desirable and something that we'll expect you to implement when you are implementing your hierarchies in the project. And that is the first thing. I mean, if you are giving me a demo, I'll ask, is your hierarchy extendable? What would you have to do if I added this? You don't have to add it in your code, but tell me what changes would it need. A good hierarchy will need no change. That's what you want to think about. So designing is as important as coding. That feel you will start getting now with the project. Our assignments were too small for that kind of a field. But designing a hierarchy is a super important job. Okay? Because if it is extendable, then great. Just keep adding. Because in terms of code, what does that mean? Create a new class and say my parent is graduate. That's it. It already exists. You write only the part that you need to. There is nothing that has to change. Okay? So that's another important characteristic of a hierarchy. And the third thing is you could add new attributes or behavior in existing parts. So if you decided that master's student in computer engineering could do something more than what he or she has been doing till now. You want to add a behavior to it, then you should be able to do that. Okay? So those are the desirable properties of a hierarchy. Then moving on to polymorphism, at this point in time, I like to just give you a very brief idea of what polymorphism is, but I would like to defer it to when we come to polymorphism. So theoretically, I'll tell you what it is, but basically for polymorphism, a requirement is the existence of inheritance. So polymorphism works in this kind of an environment. So therefore, I will tell you what polymorphism is, but I would rather have you strong in inheritance before we bring the more technical aspects of polymorphism to work. Polymorphism, why it exists under generalization is, and I don't remember if I have mentioned this before or not in this class. Basically, at 4:15 I could say class is over, right? I'm using the same 3 words for all of you. You are hearing the same 3 words. Do you all do the same thing? Do you go to the same place? No. It just means that, okay, carry on your next activity, whatever it is. So each of you exhibit the behavior that was required of you after this class. That is polymorphic. I made the same function call. I used the same words, but it can result in many different behavior. I didn't have to individually tell all of you, you go and do this, and you go and do this, and you go and do this. So in terms of software, what it means is, when a function call is made, at runtime, it can be decided what behavior will be exhibited. And it could exhibit different behavior at different times, the same function call. So let's say a function call is being called in a loop. Different iterations of the loop can make that function call exhibit different behavior. How will a function call exhibit different behavior? Is the same. Remember, it is a related concept to overloading, but when we come to polymorphism, I'll show you how it is different from overloading. Overloading is the same function name, right? But the signature is different. So the function call, right, is to a different, it looks same but is not the same. In polymorphism, you will see the function signature has to be the same. It's a requirement that the function signature will be the same. So what we are saying, actually that same function call is exhibiting different behavior. How it happens is because that function call ultimately links to different functions. But how do I decide it, right? There is still this idea of ambiguity. How do I decide which one, right? So then you say that the object calling that function could be different. But if the object is different, then I know forever. If it is object A, depending to which class it belongs, that's the function that is called. How can it exhibit different behavior, right? So then as we go from inheritance to polymorphism, the reason inheritance is needed is, you will see that a pointer to a UB student, okay, a pointer of type UB student can point to an object of type UB student, an object of type undergraduate, graduate, anything under it. And the function, when called through that pointer, therefore, could be a function called by any of these objects, depending where that pointer is pointing to at that point in time. So that is how, I'm giving you a little technical background to polymorphism. If it feels very difficult right now, forget about it. Just know that polymorphism means a call to the same function can show different behavior at different iterations. It's the same call. That's what is different than function overloading. Okay, just know that much. I'm not going to ask you any questions on that. You know, if you are leaving something, this has a very low chance of appearing on the test. I will hold it for the final exam. The only possible question about polymorphism that can come on the test is if I asked you what are the 3 different forms of generalization. Okay, so just know the term polymorphism. I won't ask you anything else about polymorphism. So that's a slide you can skip for now. Okay, as you are preparing for your midterm. It gives you the definition of polymorphism. It says polymorphism is defined as the ability to manipulate objects of distinct classes using only knowledge of their common properties without regard for their exact class. It is a means of generalizing algorithms. Okay, and goes into dynamic binding. But as I said, you can leave that slide if that makes your life easier. Design pattern, right? So design pattern is defined as, it calls it, while inheritance and polymorphism, we don't have a name for a particular hierarchy, we just call it hierarchy. It could be a student hierarchy, it could be a shape hierarchy, it could be a car hierarchy, it could be a hierarchy of anything that you are trying to organize. Design patterns have names. So they are called as named generalizations. So there is a generalization with a name given to it, and that is why when we go into design patterns, we'll tell you that there are 23 design patterns and each of those 23 have a name. Okay, so these are more like named design, is a named generalization. It does not, to tell you a little bit about design patterns, let me use the example right here so that when you look at the slides it makes sense. So they use a client-server pattern. So let me draw it for you here. So here is your client, here is your server. The client would send a request. Here is the connection. Okay, so request travels in this direction, and then the response travels in this direction, or reply. And this, the name of this design pattern is a client server design. Okay, here's an example, for example. So what are the things you know about a design pattern? It will have a name. It will tell you the components of a design pattern. So if I'm looking at the client server, it has a component called a client. It has a component called a server. It has a connection. It has request and response. So it has 5 components. What will these translate to if you were implementing them? You will probably define 5 classes so that objects of these can be created as needed and used. So typically a design pattern will have a name. It will have the components. It will also tell you when can it be used, right? So it tells you what kind of problem you would use for and what is the solution in terms of the components. And then it will tell you the merits and limitations of it. What are the advantages of using it and what are the shortcomings or limitations of this design pattern. Okay, so those are the 4 things: name, problem, solution, and consequences. In terms of this one, here is the name, client server. The problem could be providing service to possibly multiple clients in a loosely coupled manner. It has 5 elements: the client server, connection, reply, and request objects. And what is the consequence? And it says the collaboration is defined by, just as an example, sequence of events beginning with the generation of request by the client, transmission to the server, followed by generation of the reply by the server back to the client. Advantages, it may be implemented on different machines. Server may be made available to multiple clients, more than one, and all, but the limitations is it is typically a one-way street. So a client can send a request and keep sitting and never have a reply. So it can be left hanging. Okay? Unlike a bank transaction, it is committed only then, so it has a different kind of a design pattern. We can't leave you hanging, right? Saying that you don't know whether it got credited or not credited, kind of. So that kind. So it does not use a client server there. So again, as an example, no. And then I like this slide, which is slide 28 out of 30. If you want to make of a note, I will make a note of it. That to me is like the only philosophical slide that we look at in the course of the semester, and it says that think of object-oriented programming as a design pattern. So bringing the concept of a design pattern to a very abstract level and saying, what if we said object-oriented programming is a design pattern? So the name becomes object-oriented programming. When do we use it? What kind of problems does it solve? What are the components? What are the advantages and what are the limitations? It's not actually a design pattern, but just bringing the idea up to object-oriented programming. Yeah.
So this design pattern, is it only a set of guidelines, or is there any class or any?
So as you will see, it's not actual classes, no. It will tell you, so for example, here what it is saying is that you have these components, which is pretty much saying that how are components constructed in C++ or in any, again, design patterns is a general idea. It is not specific to C++. Okay, so C++ is a language that could implement a design pattern. So therefore it cannot come as classes. So it comes in a more generic description. But then typically, because we use a lot of object-oriented programming to implement these components typically mean you have these classes, and then it will say it would have these attributes and behavior. So depending on the language you decide, how would you implement these components, and what would you use to implement the attribute and the behavior. For us in object-oriented programming, this becomes classes and data and methods.
So it's simply rules.
It's not rules, it's a structure, a description of the structure. Okay. That's why that is where I was drawing the similarity from a template. It has nothing to do with each other. But just like template specified, this is how you will create this function when you need to. Here is the basic structure. So that is what it is giving you, the structure of this. And then you will implement, you will bring your bricks and mortar and make the structure actually. It gives you guidelines to do that. Okay. I would not call it rules. I would call it guidelines. Rules is like forcing, enforcing something. Guidelines is, helping and showing you the way to construct something. You can add much more than what is suggested. Okay, so it depends what part of it you are saying. Why were design patterns made in the first place? Did the programs and the software come first, or design patterns come first? No, the software. When we started seeing a lot of similarities in the problems we encountered and the software we were writing to solve these problems, we said, wait, although these 100 programs have been written by 100 different people, here are the common things. It's like the inheritance kind of a thing. Here is a lot of these people are doing common things. So experts in the field sat down and said, you know what, this seems to be addressing these kind of problems. And they abstracted out these commonalities and came up with this set of 23 design patterns. And now we as students, it feels like it existed and we are learning them. But how did they come of existence is from the idea that a lot of this software is showing so much commonality that it made sense to give it structure to this common knowledge. Okay, so that's what. So in this case, unlike the chicken and the egg, we know that the software, the design patterns were an abstraction to help us or further streamline the art of programming.
But when implementing a software or something, we do have to go in for the design patterns first.
Yeah. So if now you decide to write a solution to a problem, so one of the first steps you would do as a programmer is see if you feel that is something that has been done in the past or has been done a lot, you might want to check, is there a design pattern to guide you along so yes. Now the newer software will use design patterns as a guideline. But originally, how did the design patterns came to be is because a lot of software was showing these commonalities. More than the software, the problems they were addressing. And then people were, it's like, like if I take a very naive example, your assignments, right? Assignment 1, for example, was a problem. We had 40 implementations of that. There were commonalities, right? So, or let's say the first time I give the assignment, right? And I just give you the assignment and I see a lot of commonalities. So next time when I'm teaching, I say, this could be a possible structure. So first, from the first set of people who did these, I saw a lot of commonalities and I said, okay, maybe the students think that way. So if I give that as a guideline, it might help them to do that. So from that software, I took out a design pattern which I used in later offerings as a guideline. So that is what is the story about your design pattern. Again, know the basics. I don't care if you, not too many tricky questions on design patterns either. What it says, so here is the interesting thing about the philosophical slide I was saying. So they're saying, if we think of OOP as a design pattern, it's a pattern for object-oriented design. It is expressed in terms of classes and objects. The elements of the pattern are represented by classes. The relationships among elements are defined by association, aggregation, and or generalization like hierarchy. And the responsibilities and collaboration are understood in terms of behavior of each class. So, it kind of brings the terminology to that point. And this is a slide that I don't like, that I don't have. This would have been good if we had the projector. So let me put a so what they are doing is we have one column where there are the strategies, the other column that talks about object-oriented software structures, and the third one as the software engineering goals. So remember that first slide where we talked about simplicity, modularity, modifiability, extensibility, all the goals that are part of this column. Okay, and here is your abstraction, separation, composition, and generalization. Okay, so for example, if we take abstraction and separation, right? Where do we use it? How do you see it in action? Where? does it achieve?
Modularity.
Modularity is one. So it's not a one-to-one mapping, it's a one-to-many mapping. But that is what that slide shows. Okay. Similarly, composition, right? Composition could be done by classes, composition could be done by interfaces. That's what is about composition. Again, it uses three goals which are basically mapped to everything is reusability, extensibility and flexibility. But that is the idea, to see where we are using these strategies, what form they take and what goals they are achieving. You may agree with every mapping there, you may not agree with every mapping there. You may see other mappings that are not there. Okay? As long as you know why you are thinking what you are thinking, if I'm asking anything there to show me or tell me, just know you have a reason of what you are thinking. Okay, it's not about, that's one possible example, but that it's really a soft line that is there. It's not, don't memorize that slide is my point, but see what it means there. Here is another one that I typically is difficult to put on the board. Let's see how we want to do this. So what you have on that, this other slide is basically a x-axis and a y-axis. Okay, on the y-axis you have all your strategies. So you start with your abstraction, your separation, move on to composition. Again in composition, first your association, then your aggregation, then you go to generalization in the order of inheritance, polymorphism and design patterns. And so here are your strategies and here are your software structures. Okay, so classes, your you have your using existing classes, creating new classes and patterns of classes. Okay, so existing classes, did you use a single existing class, many existing classes, single, you created your own class, you created many of your own classes in your program, or you started using design patterns, right? So let's say if you are using an existing class and you are doing only using a single existing class, then what strategy you are using? Okay, many, you come to composition. Same idea with the, you are writing your own class and you are writing many of your own classes. This is where the several is where you will get to the aggregation. So you will see basically a kind of a milestone like this. Okay, so what you have been using and what techniques you have been using and where you are. We are pretty much at this level. If not here, definitely here. You have definitely, I mean, right from assignment 1, you have done 2 modules. So you have written a single class of your own, even if you did not do several of them. So, and here you have definitely used association if you haven't used aggregation. Okay, and then moving forward now, we will do the generalization into the design patterns and move to the several classes created by us to the patterns we are using. Okay, so there are these 3 milestones that are left, but you have reached that point. So again, look at that slide and I think it should make sense as to what. Again, if you have any questions, feel free to ask me, send me an email. As I said, sent out an email earlier, I will be on campus and available instead of today's office hours tomorrow between 2 and 3:30. If that is not convenient, send me an email, I'll be happy to if you have any questions on this. That leaves one slide that I had skipped earlier, which was about an interface.